All right, let's get started. How's everybody doing? So as some of your colleagues asked me the previous session, which part of the book are we, teaching on every lecture? So we mostly finished with the chapter 1, except the Hefting inequality, which is going to be for your theory for the after your midterm. So we can skip that part. Except in that, we already done the chapter 1 of the book, your textbook learning from data, and then mostly chapter 2 would be for the parts of your after your midterm. We've already started the linear model on the chapter 3. So today we're going to be discussing more about how we're going to represent the input, and then linear regression as well. I'm not sure if you're going to make it for nonlinear transformation, but yeah. So linear regression would be mostly the job of today, and we carry on with the least square for the next session. Also, are you attending your tutorial sections? Because there are problems that are very important, so you better attend. Like one of them was, I guess, 1.3. So let's see. Yeah, 1.3 is an important problem. Yeah, learn it well. Another thing is, as I mentioned in the previous session, I uploaded the slide under slides for your own section. So in order to avoid any confusion, I renamed this slide to skip slide 5 to 13 because those with the Hefting's inequality. I mean, it's good to know it at this point because you understand what the E of in, or if you see somewhere E of out is, but mostly we're going to discuss about it after your midterm. Also, I started to upload the videos of the lectures in a playlist of the course. You can refer to my announcement for the link, or just Google this EC 421, EC 1513 on YouTube, or just Google it by my name, you're going to find it. All right. Let's see how we're going to, today we're going to talk about how we're going to represent data from some of the well-known data sets. So I brought two useful and well-known data set. One of them was MNES data set, which was the work of Jan LeCun, who is the AI director of Facebook now. So it's a data set of handwritten digits. So it has 10 classes from 0 to 9. So 0, 1, 2, 3 up to 9. And then these are some of the examples of the data you might see in that data set. You can download it here if you want. I left the link here. So this is a good data set if you want to start working. I'm pretty sure you're gonna be working with your assignment somewhere down the line with this. Another close example was the data set of the apartments number. So a street view. Here you can see the street view house numbers. So SVHN. And also here's a link from Stanford. So this is a little bit harder with respect to the other one because some of them are not handwritten digits, and also you have other things, other sort of backgrounds in your frame, and some of the numbers, which can be mostly, are not only in single digit. So you have to apply multi-class classification if you want to, predict the label. So for now, we have a quick example of the MNES dataset, how we're going to be able to represent that as an input to our linear model. So if you represent one of the digits, like digit 1 here, like one of the handwritten digits, like this, it mostly, so in this case, this one was 28 pixel, so I just drew some of the pixels just for your information. Also, the length and the height, both of them are like 28 pixels. So your majority of information is happening somewhere here. So some of the pixels can capture that. So what we are interested in is a way to input this representation in a vector format. So later on we use it as an input to our model, right? So our input would be each of the images. In this case, that was a handwritten digits of 1. We have 28 by 28 pixels. So in total, and also including that artificial coordinate that I have been talking about. So we're going to have 784 pixels, which represents our number of representation as input. So as you see, it's a pretty long feature vector for such a small problem, right? Because if we want to later on add it to our linear model, we have to have another 784 W's for that. And just a prediction, learning a model through this is going to take a long time. So just like that, because you have to have the same number of these for your weight of the model as well. So can we reduce or downsample the features in a way that we gain most of the information, we still preserve most of the information, and avoid doing almost 700 something pixels? So there are other techniques in machine learning that we're going to touch on that after your midterm, like PCAs, how we're going to downsample your input representation using PCA or density estimation, or recently autoencoders. But for now, there are other tricks which are very easy. You can downsample your raw data, which is this. This is called your raw data, to a more representable data. So one of the features you can define in order to avoid that 700 something is, if that specific pixel or that specific character in general globally had intensity or not, or what level of intensity it had, like you can number that intensity, or was it a symmetric digit or not, or was it horizontally symmetric, was it vertically symmetric, or even in diagonal way. What was the sharpness? So these are all the features that you can define to avoid having that raw data and downsample your model. So suppose we take only 2 of them. In this case, we took only intensity and also symmetry, and that was still our x0. So you see that our linear model shrunk a lot from 784 up to only 3. And we'll see that still with these 2 simple features that we downsample, our model is still able to predict somehow in good level and distinguish between our input representation.
What do you mean by symmetry?
Like if the right side of the right portion of the frame is, like if you flip it, you're gonna have the same symmetry or not, or it could be like the vertical version or the diagonal version, right? Or other thing you can define for yourself as well. Why is the number of bits?
Number of bits in the new model, like 5 from 0 to 256.
256? Oh right, yeah. Oh, that was a mistake. Correct. Yeah, it's gonna be the same size. They all fixed it. Yeah, I'll put a note here. It's really nice that I can edit the videos afterward, because I can remove all these typos later on. It would be great like we had a life like this. Yeah.
Why do you need? Is it like you have to use 28 by 28 pixels to represent data?
No, in this specific case, that MNES data set, if you download the photos from here, this website, that was built on a data set of some thousands of 28 by 28, and that model that was well known by Jan LeCun, which we might touch on, and it's called Lenet 1 up to Lenet 5. That was accepting this 28 by 28 as the starting point of this convolutional neural network. All right.
So symmetry is mean for every pixel or the whole image?
In this case, that was a whole image. Like for the character that we are interested, like 1 or 5 or 6.
So the value for every pixel will be the same, right?
Yeah.
Symmetry.
Yeah. Actually, when we use these features, we don't have any pixel value anymore, right? because we don't have that 700 pixels. All right, is it clear? So let's just have a look at an example of a binary classification between two digits, like case of ones and case of fives. Let's see what was the linear model that we trained, performing. So on the right side, you see some of the examples of the ones, and they are mostly generated with the blue here. So these were supposed to be for 1. And these are the distribution of the training examples we could classify for the 5s. Believe it or not, this meant to be 5 in one of the training examples. That was, of course, misclassified. I'm pretty sure even a human wouldn't be able to classify it well. But sometimes these mispredictions happen. So you see that still with those two different features like symmetry and intensity, we could be able to classify them both ways. So like in 1, we have normally more intensity because we are occupying more of the pixels of the frame. And that's why most of the cases, like this case, which was a smoother or better 1, they were inside the rest of the data. But this one was a very poorly made 5, was misclassified because it was sort of an outlier. But like these two were like some good examples of 5, and they were still within the cloud of other classified 5. So our job is to now find a linear classifier to classify them. So let's see how well our PLA that I described 2 sessions ago performs here. So we are interested in taking a look at in-sample error, as I mentioned in the previous session. So this is our metric of interest for now. We don't care about E of out, which anyways you know already. So using those 2 features, which was symmetry and intensity, average intensity, so our PLA, the final value after 1,000 iterations stopped here, which is not a perfect line. You see, we have some good classifications here. We missed 1 point here, and also we left out all the points here, which is sort of 15-20% of the population. So we have at least 20% error rate. And you see, starting from the iterations from 0 to 1,000, when the PLA algorithm was trying to, search for misclassified point and change the line for the classifier, at some point we hit a very good point, like at around 250. You see our in-sample error was even lower than 1%, so it was 0.5%. And then after some iterations, probably at maybe 400, by picking one of the misclassified point here, it went all the way back up, and also it went even worse to 500, and it couldn't recover somewhere better than this. So like it stopped here after 1,000 iterations. So what was your question?
Sorry, why do we not care about the out-sample? Why do we care about the in-sample?
No, because in-sample is your loss function that I described in the last session. Remember, as a loss function, the in-sample was a sample that we took out of our distribution, right? And this is what we train on. Out of sample error is very important, but for now we just focus on the in-sample. Out of sample help us to define a complexity of the model. You're going to see later on for your pack learning and VC dimension. Yeah. So now we see that at some point we hit a very good point, but then we lost it again. Couldn't we sort of save that good point that we hit here? It might be like, it could have been like this line. That could have been this line that we had like in iteration like number, 100. That could have been this line here. and then later on, when we went forward, we missed it. So there is a technique in PLA, and because of its name, you can understand what does it do is pocket algorithm. So when it finds a good solution that outperformed the previous solution, it just put it in its pocket. So like saves it, and then for later on, if a better solution found, it's going to replace that. It's sort of a intermediate buffer just to save the best found results. So let me be out of this. Okay. So when to use the pocket algorithm? As you see, one of the things that hindered our perfect classification was the point that the data set that I show you, that the training data between 1 and 5, were not linearly separable. I'll show it. I'll bring it back to the slide so you can have a look as well. So one of the perfect cases that you can use pocket algorithm is since your data you were targeting was not linearly separable, so PLA won't stop. It's going to iterate forever because it can't converge. It's going to find another misclassified point, and by switching the line towards that, it's going to misclassify other points, and this vicious cycle carry on, forever. So pocket algorithm, save the best found model, so at least we won't go worse than what we've been. Okay. All right. So it basically keeps the best vector found at iteration t and puts it saves it in a pocket, and it replaces it. So this is replace. It replaces it if a better weight vector was found. So let me just describe what the algorithm was. So at step 1, we set the pocket weight vector, or W hat, to our initial weight of 0 that PLA found. So it's sort of an initialization. On the second step, we enter a loop for iteration from t from our first iteration up to t minus 1. We're going to do these 3 simple tasks. So 1, we're going to run PLA for 1 update to update our W. So now our W becomes W of t1, t plus 1. And then we evaluate,
So what does it say beside W0?
W0 of PLA. Yeah, I apologize for my handwriting. So we run PLA to update the weight to W t plus 1, and then we evaluate PLA. And we evaluate the in-sample error of the weight, and that's at that point t plus 1. Then, if the in-sample error that we found here was having a lower error rate than the one we had already in the previous steps, so we're going to assign new value for our W hat, and the value would be the W t plus 1. So we basically update the W hat. And we exit the loop when the iteration is finished, and we're going to return W hat at the end. Okay? All right, let's see by using this. Let's have a comparison between having a pocket algorithm with PLA or a pure, vanilla PLA. So what's going to be the difference here? Yeah. So that was our in-sample error of PLA on the left side, you see. And the pocket algorithm saves this point that had the lowest found error in-sample error at a time. And since we didn't find any better points, it stayed there up to the last iteration. Thus, after a certain point, we won't go back in a worse, place. All right. Also, let's see the comparison. So again, the PowerPoint messed up here. I think it's so. This was supposed to be your PLA. You see these are different now. So using pocket algorithm, you had a better classification, except those two mispredictions, like as an outlier. The rest are sort of seems good. And you see, our data wasn't a linear separable data because with no line, we couldn't separate these two data points because we had this and also this sort of mixed with the blues. All right, is it clear? Okay, let me just go back and touch on a theorem. So you're gonna see the proof of this theorem in your tutorials, and it's called Rosenblatt theorem. So Frank Rosenblatt was the researcher, U.S. researcher who built the first perceptron machine in if I'm not wrong, 1956 or 57. And so you can just Google that and see how huge of a machine it was. So that perceptron machine was able to classify images using a very basic perceptron algorithm. And he, through this theory, he sort of touched on the upper bound of number of iterations that a perceptron learning algorithm on a linearly separable data set has to do on a given data set. We call it D. So it would just suggest an upper bound for the number of iteration PLA has to perform in order to converge and terminate at some point. And that's the upper bound. So R divided by P raised to 2. So our R can be defined by a max of the xn raised to for the n's from 1 to n. So it's sort of a radius for our problem. And our P can be calculated by the transpose matrix of W multiply xn, and that's the output of the PLA. So intuitively, you can see that R represents the radius of our data set, and P was the distance, and W star was the margin. So this is sort of an upper bound of the number of iteration a PLA has to perform in order to terminate for a linearly separable data set, and you're going to see the proof in your tutorial sessions.
In the top of the description, what's the last word in almost?
Yeah, right. So it's almost. Let me just.
Is R the square of the infinity mark?
Is RDD a square of?
Square of the infinity mark?
Are you talking about here? Here? Or here?
Yeah, that one.
So is RDD a square of infinity?
The infinity mark.
Where is the infinity? No.
Like the maximum value of x, and then you just square that. Is that what it's saying?
No. Xn is the last element from 1 to n in our data matrix. So like D represents. So let me try. D was representing our x1, y1 up to xn, yn. So the last one was like from 0, 1 up to n, right? And this is for each iteration. So like the max value of x. Yeah. All right. Let's go back to. So now we learn how to classify using a linear model, which was Perceptron and some variants. Now let's discuss the linear regression, or LR. So what if our classes were not binary, or were not discrete numbers actually? So can we still do predictions on them? So it's mostly the definition of classification versus regression. So regression is one of the you can find it everywhere, like mostly one of the most well used techniques. Let me exit again. Okay. All right. So let's go back to the credit card application again. So let's revisit it. So we had an application info, and many of them to n. So using some features like age, gender, salary, current debt, and so on and so forth. So using a classifier, we could classify them either +1 or -1, which corresponded to either approved or reject the credit card. So that was the classification, so the credit approval, right? On the regression case, instead of +1 and -1, you would like to see what was the real value, what was the real threshold for that specific client of the bank, so that after that threshold, or that specific threshold, if that user hit that threshold, was enough for us to approve the application. And that's a number now. That's a real number. It's not a discrete value anymore. So as an input, we have. Let me get rid of this. So as an input, we have the customer representative features like age, salary, etc. So starting from x1 up to xt, and we add that x0 as well. So the linear regression output is our hypothesis h of x, which is a summation of all weights multiply xi's. And if we represent it in a vector format, it's going to be W transpose multiply x. So now we're going to see how we're going to derive to that point and how we're going to minimize the error rate in a regression problem. Okay?
So here D means the dimensions, right?
Yeah, so this is basically this. This is the, so that would be D, and you have many of those. You have many of those, n of those, and the whole thing here, the whole chunk would be your big D, right? All right, so we're going to call linear regression LR. In our training set, our D would be our data set x1, y1 up to xn, yn, and all the xi's are from a d-dimensional space. However, the most important difference between a regression task and a classification task is our label, y labels, are now from R space, so they can accept any real number. Whereas the classification, in our case, was a binary value. We could have multi-level or multi-class classifications with so many different, classes, just like the MNES data set that I showed. If you were to predict on all those 10 digits, all the 10 classes, so it would be called a 10-class classification. But here, our Y accepts R value, so we are actually predicting a real number. So in a 2D data set, it's as if you're fitting a line into your data points. So like you have a point, so many points here, your D. So like you have points here, here. So that the task of linear regression would be to fit a line so that it minimizes the in-sample error. So that these values, when you sum them up and square them, this would be the lowest, so that the best line would fit in the middle of all your data points. I'll talk about it more later. So for the training set, we have the D matrix, and then for the prediction function, we have a y hat of our hypothesis x as the estimate of y given our x's from our d-dimensional space of R. As per our linear model, so our hypothesis would be h of x w0 plus w1 x1 up to wd xd. All right, on the w side, the vector of w, we have it from w0 up to wd, also from the x vector. It is from x0, x1 up to xd, and that was the transpose. So, and as you knew, our artificial coordinate was having x0 equal to 1. So we can simplify it at the end. This is I equal to 1 from 0 up to the wixi. Okay? All right. So we need to, take into consideration a very important criteria, and that's the minimization of our in-sample error. So how well we can fit the line so that we have a minimized error. And so for that, we need to compute the average squared error for our, E of m here, E of m of w, which is like the average, just like what the name is. So you're gonna average the squared error. So you're gonna average the squared error of all those points to your line that you fit in a data set. So that's the criteria. There are so many techniques that do the job for you in this situation. So we're going to touch on some of them. There are other things as well because it's a very well-known and well-studied model, and it's been used quite often everywhere. Like probably you have heard of feeding a line or feed your data with a line somewhere before. So it's been pretty common use. Okay, so we call this value, each of the values of the difference between yi's and your multiplication of w's and x's, e of I of w. And it's basically this, so an e of I of w, which is this value, is the square error on ith training example. So at each of the steps, we can calculate this e of I of w. So given our data set D, we find W from our R plus in a D plus one-dimensional space because we added the artificial coordinate. And we want to minimize the E of the in-sample error of W, right? So that's the job. So there are two broad categories of optimization for that. First one is the analytic solution. So this is analytic. So like using, and normally we use gradients. So D to do that. The other one is like the geometric intuition. So using intuition in geometry, how we can project our y hat. So I'll describe it later now. So let's start with the analytic one. So in a two-dimensional space, as I described, so you're going to have to calculate your EIs at each iteration. So these are your data points, and that was the line you fit. Sometimes they call it L as well for the line, or just W. And if you go into higher dimensional space, I mean we can represent a 3D dimensional space as well. So your line, your L, would change to a space or a plane. We call it hyperplane. So that's going to be the hyperplane of linear regression here in 3D space. And as you see, your regression is always d minus 1 in dimension. So if you have a 2D space, that's going to be a one line, 1D, which is the line. If you had a 3-dimensional space, that would be a hyperplane, and that's a 2D, because you have one dimension here and one dimension there. And for the high dimensions, which we cannot describe it visually, you're going to have d minus 1 again.
So excuse me, so Regression always means that we have to dump one dimension, right? Like from two.
No, you can do any dimension. It depends on the dimensions of your data and x and y's. So, I mean, it depends how many parameters you have. Like here you have 2 parameters, like x1 and x2, so it's going to be total up to x3, right? If you had 20 of them, it would be a multi-dimensional, you know, in a higher dimensional space that you couldn't, you know, visualize it. But for just visualization purposes, we just had, if you had only 1x, so that would become a 2-dimensional. If you had 2, it would become, you know, a 3-dimensional space, right? Like think about these two as your intensity and symmetry that you had in an example. All right, let's have a quick example. So our X is advertising cost in 1 week for a company. So this is advertising cost in 1 week. And your Y is sales. This is sales. Hope you can read it. Sales in 1 week. So given our historical data from D, and our D is 1 only, so suppose this is this case, the case on the left, you have only 1, so it's going to be 2-dimensional. We need to feed a linear model, Y equal to W0 plus W1X, for our data points. So these are our data points. Here. And that line, which we represent by L or Y, is going to be a regression line. So the x-axis pertains to cost, and Y represents the sale. And that was our artificial coordinate. As you see, it's always pointing to the x equals 0. Yeah, so that's your Y. All right, so our W0 would be the sales when X was equal. So it acts sort of a bias for us, how well up or how well down we were starting. And W1 increases in sales for unit when our unit increases in cost, right? So you see, it's going to be a pretty simple model. We have only 1x, and that's going to be the sales in 1 week. So if you want to refine this model and add more features into it, so that we sort of break down the cost that we have and not just represent it in just with 1x, we could just go for 2 or 3 more features as a refined model. So our refined model could have been 3 x's, x1, x2, and x3, and that would have referred to the advertisement cost for our TV, or I don't know, advertisement in TV and media, and then you had the advertising cost on radio stations, and then you had another one as an advertising cost on your newspapers and text. So in that case, your first Y becomes W0 plus W1, X1, W2, X2, and W3, X3. So of course, the largest W points to the most profitable X1. So now, given a regression problem, how are we going to be able to minimize that error, in sample error that we talked about? So we're going to end up in a linear systems of equations. depending on the number of i's we have, like I from 1 to up to n. So we're going to have a linear system of many equations. Just like this, our yi is going to be w0 plus w1 xi1 and going up to wd and xid. So if you have like 3 i's, so you would have 3 lines of this with some x's. In this case, we would have 3 x's, so 3 parameters, and 3 i's, so like 3 lines like this as y1, y2, and y3. So normally your column, number of columns is going to be the number of, let's see. So here, the number of columns you have is the number of variables you have, this is of, and it's d plus 1. In this case, you had this, you had, oh sorry, so in this case, that would be your x's. And then here, the number of n were corresponding to your I. Okay, now, given these two hyperparameters, if you will, we can define two different situations. What if our d was bigger than n, or vice versa? What would be the case? So if d plus 1 is greater or equal to n, so that means we have more variables, at least rather than number of n's. So definitely an exact solution exists. And here we can use a linear system solver that we're going to describe one of them to find the gradients that I mentioned using the derivatives of your function. But if not, if it was the case otherwise, no exact solution can be found that find the optimal solution. So we have to go for approximations. We have to approximate the function by minimizing the summation of this, which was the regression function. And unfortunately or fortunately, in most of the cases in machine learning, you have many data point, and this is like huge. You're going to have a big N, and you're going to have a smaller D's. You have like 5, 10 features, and maybe 1,000 lines, 1,000 data points of history, right? Just like you're thinking about your credit card application, you might have 2 million customers as their historic data, and you have like 50 or 100 features representing those customers with like age, gender, maybe residency, years in residency, current debt, and so on and so forth. So your N would be way, way bigger than your D. So in most of the cases, we end up approximating the problem by minimizing this function. And you're going to see some examples this session, also next session, also in your tutorials. All right. I'm running out of time, so I guess I stop here, and we picked it up later. So, and as I described, we try to point out to the specific chapters that each week you have to, you can read if you want. Also for this lecture, if you remember, we had another textbook for that, by Boyd and Vanderberg. So this section accounts for the chapter 3, section 3.2 of that textbook, if you wanted to have a look. But I'm sure we're gonna put an announcement so that you have them per week. Okay. Have a good day, guys.